Okay, we're going to do the problem of calculating gravitational field inside the Earth if the Earth is uniform density. Okay, so first part, use Gauss's law, determine the acceleration of gravity inside the Earth. Okay, so here's our Earth. Just drawing it in 2D, right? But this is a spherical object. Okay, and so our Gaussian surface is going to be somewhere in between. It's going to have a radius little r, so somewhere in between 0 and the edge of the Earth. And it's going to be a sphere as well, right? So it's got to be a closed surface, and we're going to just look at what's happening inside of that. So Gauss's law says closed integral of g dot dA over my Gaussian surface is negative 4 pi g m enclosed. Okay, so the problem says that the Earth is a uniform density, not quite right, but we'll take that as part of the problem. So our density rho is in general mass over volume. So in this case, it is the mass of the Earth over the volume of the Earth, which would be 4/3 pi radius of the Earth cubed. Okay, so then my enclosed mass will be 4/3 pi little r cubed, right? So that's the area inside the shaded sphere. And now I have to multiply by the density of the Earth. So I can plug that in. 4/3 pi little r cubed times my density, which is the mass of the Earth, divided by 4/3 pi re cubed. Okay, so my 4/3 pi cancels out. And so I get that the enclosed mass is me over re cubed times r cubed. So that's something a lot of people did not write out specifically. Okay, so now we can go back to Gauss's law. So we have integral of g dot dA is minus 4 pi gm enclosed. Again, we're going to do a Gaussian surface where we think there's going to be symmetry. So anywhere along the surface, the acceleration of gravity should be the same, right? All that should matter would be our distance from the center. So g comes out as a constant. We integrate around the surface area of the sphere, so we get 4 pi r squared. And then we have minus 4 pi g m enclosed, which is me over re cubed r squared. Okay, so I have a 4 pi on each side. That can go away. And then I'll divide by, sorry, this is r cubed. Divide by r squared. So I get g is minus g me over re cubed times the radius. Okay, so my acceleration of gravity is going to increase linearly with r. Okay, so that's part A. And then B is show that the equation of motion in this region takes the form of a harmonic oscillator. So remember, g is an acceleration, right? So it's a measure of how quickly my radial distance is changing, right? So my acceleration in the radial direction. So g is equivalent to saying it's my acceleration in the radial direction. So this equation says acceleration in the radial direction is minus gme over re cubed times r. So this is the form of a harmonic oscillator, right? So we have this is a constant. My acceleration is proportional to my displacement, and I have this negative, so that's the linear part. And then I have the negative sign, which means it's a restoring force, trying to bring me back to equilibrium. So a linear restoring force gives rise to simple harmonic motion. Okay, and then, so part C, determine the expression for the oscillation. You don't need to calculate it. Okay, so C if we look at our general simple harmonic oscillator, we have something like x double dot is negative omega squared x. So that means our constant here is omega squared. So omega squared is gme over re cubed. And then our period is 2 pi over omega. So here we have omega is square root. Okay. And then our period is 2 pi over that, so 2 pi. And then we have the square root of re cubed over gme. And that's it.